Hello everybody, and welcome to the presentation about the extreme temperature efficiency. My name is David, and I'm the responsible product manager for refrigeration packs and systems for the ETE group. The extreme temperature efficiency, ETE, wants to solve two major issues we see today. One is that energy costs, we all know that also in your privacy probably, the energy costs are exploding currently. And of course also when you are running the refrigeration packs, energy costs is more and more a big issue. So we want to support you in case to find energy efficient solutions. And the other one is that we have seen also this summer that in regions where normally we don't have very high ambient temperatures, even here we had spikes in temperatures more than 40 degrees, more than 45 degrees. So we also want to support you with solutions which help you to run a sustainable and reliable system even in very hot ambient conditions. And today I would like to explain to you how the extreme temperature efficiency works and why this is very useful in my opinion. So let's have a look very quickly on a transcritical booster system. We see medium and low temperature applications, low temperature compressor, medium temperature compressor. We have the gas cooler, we have the transcritical valve. Then we have a receiver where we separate gas and liquid. The gas is going directly to the compressors, going sucked again. And the liquid goes to the application where we evaporate the liquid to gain the refrigeration capacity. So first of all, I would like to explain to you what happens when we have very high temperature in the system. So when it's really hot, let's say 43 degrees, as in this example, then we have a gas cooling outlet temperature of approximately 45. So normally we have a 2 Kelvin difference from the ambient to the gas cooling outlet. Then we go to the high pressure valve, and then we have the liquid receiver. So what's happening in the system when we have these high temperatures? I try to highlight a little bit the isotherm of 45 degrees. And when we go up to 100 bars, then you see we have approximately 63% gas in our system, which means this is the gas which runs through the compressors. But at the end, we don't have any refrigeration capacity because we don't have the liquid left, which is used to evaporate and makes the cold temperature in the cold rooms or in the cabinets. So what we can do, you see the isotherms are really flat on top of the critical point. So we can increase the pressure level, which leads to more liquid in the system. So this is a good idea, but you can see the more left you go, the more vertical the isotherms get. And also we have some physical limits in the high pressure of the components. So we cannot increase the pressure to an endless level to get more liquid in the system. So let's say 110 bar is approximately where we have to stop due to the physics. Then we can gain 50% gas. If it's hotter, of course, it's even less. So what you can do is what we see normally when it's really getting hot, then the customers have water spray like a Gardena or something like that to cool down with the evaporating of the water, the gas cooling outlet temperature. In regions where it's generally really hot, like Australia, Dubai, or south of Europe, also subcooling units are very common. These units are external refrigeration cycles and they cool down the gas cooling outlet temperature. Normally, there is used a refrigerant which fits to these high temperatures like 134A. Just to explain to you what's happening there. So we cool down with the gas cooling until the ambient temperature. And then the subcooling unit provides, as the name says, a subcooling of the gas cooling outlet. And this leads to, you see the numbers here, a significant increase of the liquid in your system. The problem, of course, is that we have, first of all, an additional refrigeration cycle. And second of all, it's running with an F-gas. And if we want to be 100% natural refrigerant, this does not fit one perfectly there. So we developed some kind of an internal subcooling unit, which runs with inside the same system. So we take partially the mass flow, expand it, and cool down the main mass flow. Then we have a dedicated compressor running on a very high suction pressure level. Approximately, we are evaporating at +10, +12 degrees. So we are having here more than 50 bar suction pressure. So this compressor is really running very energy efficient compared to standard compressors. And in this case, we are able to include the subcooling in our system. Okay, at the end, this is what's happening inside the system. We are using the gas cooler, and then we are still having the subcooling unit. Depending, of course, on the sizing of this ETE compressor, you can run unlimited amount of ambient conditions. So 50 degrees, 55 degrees, so no problem anymore. You just have to dimension this compressor in the proper way. You can compare this technology a little bit with a parallel compression. Also here with the parallel compressors, you have a dedicated compressor running on a specific suction pressure level. But the main difference between the ETE technology and the parallel compressor technology, first of all, this compressor is running even more energy efficient because the suction pressure is much higher than the parallel compressors. Second of all, the parallel compressor is removing the flash gas, what's coming out here, in an energy efficient way. It's not solving the problem that we don't have enough liquid in our system when it's getting hot. So what's happening, the more flash gas there is in the system, the less liquid is inside the system. And then you don't get an error message from the refrigeration system because the refrigeration system runs fine. The compressor all running on maximum speed, but at the end they are just having flash gas inside the cycle, no liquid anymore in your application. So you get temperature problems in your cabinet, in your cold rooms, because there's not enough liquid left to keep the low temperature level. And the very same also with the parallel compression. You are not solving the issue that here is not enough liquid in your receiver. The ETE system, on the other hand, avoids that there is flash gas happening. We have stores running in south of Italy where the flash gas valve was open only 3% of the day, which means this is more or less zero. We just need to open it occasionally to control the pressure in the receiver. But at the end, we make sure that there is no flash gas left in the system, which means totally reliability of your system in any ambient conditions. There is no problem anymore that there is no liquid left here. Here's a short overview about ETE and parallel compression, because in my opinion, it's a very comparable technology. You have a dedicated compressor running on a specific suction pressure, and it's a technology which is used when it's getting warm ambient conditions. So with the ETE, we work on the root problem, which means we avoid to get flash gas. When the parallel compression try to run with the problem and in an energy efficient way. So it's a two different thinking type of system. We are running with more than 50 bars, which means the suction pressure is very, very high. And this makes sure that the ETE technology is even more energy efficient than the original parallel compression. Here we are running approximately 37, 38 bars. The evaporators have not 100% of the refrigerant capacity left. This is what I just explained, when there is just not enough liquid in the system. So it does not really solve the problem, where the ETE solution really solves the issue. So there is no problem anymore with the very hot ambient conditions. And I think I also have some examples. We are having more than 150 ETE systems running, so it's a very reliable system. It works really well. It's not a prototype or something like that. We have in Australia, in Dubai, and of course in Europe. So all the locations where it's becoming occasionally warm and hot. I just can say we have a huge customer in France, which I was very happy with this solution. Right now, every single product we sell to this customer is including ETE because it just works perfectly. They had no issues in the summer. There was not a single problem due to the high ambient temperatures. So I think it's really interesting. Let's have the last few minutes looking at some case studies. This is an installation in Bologna. You can see the value. So we're talking about a supermarket with 150 kilowatt medium temperature. And the ETE compressor, the subcooling power, was approximately 50 kilowatt. This was the temperature profile. And we also switched the ETE compressor on and off to have a little bit of comparison, also from an energy perspective. And as you can see, when it's getting warmer, the efficiency really makes a difference if you're using this high pressure parallel compression, this subcooling unit. And what have we done? The flash gas was reduced by 73%. And I think this is already significantly. So you have the two things, what I mentioned at the beginning. We have a solution which helps you save energy. What you can see here, if it's getting warm outside, it really makes a difference if you're using this subcooling unit or not. Because of this very high suction pressure, makes more or less this difference. And it also avoids the problem that you have no liquid in your system left, that your applications just die because there is not enough evaporation power left. So we avoid having flash gas. We are having an energy efficient system, and this is more or less what we want to support our customers with this kind of technologies. What we also have to mention is that the ETE system only runs with standard components. So you don't need to be afraid that your service technician is not able to handle in case a valve breaks or something like that. It's just a standard heat exchanger. It's just standard solenoid valve. What we had to develop, and was really the trick on this whole scenario, is the oil system. So with this very high suction pressure of the compressor, you cannot just use a standard oil system. This will not work. So we have developed a new oil system. This would be too long if I explain everything here. You are more than welcome to visit us in our booth, where we can have a look on the new oil system, what we developed specifically for the ETE system. This new oil system, just to tease a little bit, works so well that we also use it now for standard packs without ETE solution. So it's a really good thing. So if you have time, come to EPTA and check out the new oil system. Okay, I also want to give you a little bit warmer case study from Australia. This is a 90 kilowatt medium temperature, 5 kilowatt low temperature, and a subcooling power of 34 kilowatt. We have reached a maximum ambient temperature of 47.5 degrees, and we were able to reduce the flash gas mass flow by 81%. So this is really a significant difference. And you can also see the energy efficiency in terms of switching the subcooling unit on or off. Okay, that's the information I wanted to give to you with the ETE. And as I said, you're more than welcome to come to our booth, ask me questions specifically to this system. We have also FTE system where we run flooded evaporators all year long. We have the new oil system. We have new modular packs. So it's really worth to come and visit us and see what's going on here. Thank you very much.